nanohub.org.
Online simulation and more for nanotechnology.
Welcome to the next session of the recitations on semiconductor education. I'd like to start out with a NanoHub homepage. Again, we really have four images in our head of what we'd like to have users be enabled with NanoHub. So NanoHub provides modeling and simulation apps and tools. We want to enable people to learn and teach with them. And we also want to enable them to do research with them. We provide tools to develop such tools on NanoHub and to then ultimately share and publish them. Just like to highlight that all these apps that I'm demonstrating, all the NanoHub apps are actually listed in the Web of Science as a proper publication. So the interest in semiconductors has been rekindled through supply chain issues and secure electronics issues. So we created a landing page here for semiconductor education and workforce development. And we have a variety of elements available in this realm. I'll focus today on this immersive learning through simulations, but we also have several courses highlighted here. We actually have over 170 courses on NanoHub, but these courses here are specifically geared towards semiconductor fundamentals, quantum transport, and thermal transport, etc. Some of these courses actually have free textbooks associated with them, so they're hosted here. And we're also starting to supply commercial software. We have MATLAB and ThermoCalc in our repertoire right now, and hopefully we will have Silvaco tools soon. The recitation series is also listed here, so you can see the recordings of the prior recitations from December to January and the ones that we're recording now through WebEx. So let me go in here on the semiconductor device fundamentals, where we want to enable to really have students immerse themselves in simulations and data visualizations of these concepts. So ABACUS is geared towards understanding semiconductors, and it reflects a typical course in semiconductors. So you probably start out with crystals, you develop band models, then you deal with bulk semiconductors, maybe shining light on a tool, etc., on a slab of semiconductor, and then p-n junctions. And today we'll talk about bipolar junction transistors, which are the natural extension, so to speak, out of a p-n junction. And then a typical course moves on MOS capacitors and MOSFETs. So today we're going to focus here on these bipolar junctions. And this tool, bipolar junction tool, is embedded in ABACUS. We have a couple of exercises associated with this on this page here in ABACUS. We also have a faculty-only page where we want to build community and host solutions and questions, etc. And that faculty-only page, you have to join and get approved. All of these other offerings we have here are free to use. You have to log in. I'm already logged in. So I encourage you to create a login. And if you don't have one, maybe I'll ask you to create one now. Maybe go up here, follow along, and create a login up here so you can actually follow along with the simulation. So that will be great. I'm going to navigate. So this is a group page that assembles all the associated content. If I click on this link, it actually gets me to the ABACUS tool. And this ABACUS tool is a publication. It has a DOI. It's been updated, so there's multiple versions of this. You can track the versions. It has authors. Here's some screenshots, and you can look at usage statistics. So 17,000 users have used it. So here's a map that we're working on improving because it looks kind of cluttered. There are citations, so this tool is actually cited in the literature. There's some Q&A and some reviews and some wishes for improvement or changes. And if you go in here and you're logged in, you can launch the tool. So here is ABACUS. It has this, say, splash screen, which overviews the tools that are in it. And these are now really links to individual tools that we have on NanoHub. All of these tools you could, in principle, also launch individually, but ABACUS sort of assembles them into one tool, so it's a one-stop shop. So today we want to talk about this bipolar junction transistor. You can click on this link, or you can pull down the link, the list of tools here. So either way, it gets you into a tool, into the bipolar junction transistor lab that actually by itself, as I said, is a tool by itself. There's a tab here that has some homework assignments associated with it. And there, as I said, there's more information on the individual tool page. One thing I always like to highlight is that this tool is running a full-fledged industrial strength tool called PADRE. This tool was donated to us from Bell Labs. PADRE did design real transistors for Bell Labs in the 90s until about 2001, 2002. So that's when we also received PADRE and started to integrate it into NanoHub. PADRE by itself is a full-fledged engine. It's actually, you have to be somewhat of a tool expert to use it. And what you see here is an app that's really wrapped around this tool. So you can look at, say, a standard one-dimensional BJT and NPN in this case, which many textbooks elaborate on. There you can do a PNP as so this is the default is this guy, the linear. Then there is a three-dimensional version, so to speak, that has actually a stack like this, and you can have 2D geometry details as well. And not only for NPN, the whole thing is also for PNPs as well. So there you go. So let me focus on an NPN, the linear version. There we go. And so here are the specs. So we have an emitter length, a base region, and a collector region. There's an associated width with this, and you can have, so this is a geometry specification. Then you can modify some material properties. So on this tab here, you can select different materials. So right now we have silicon, germanium, gallium arsenide. You can, and then modify the doping in these regions. So I'm going to start out with a sort of plain vanilla equally doped BJT and start discussions from there. On the Material 2 tab, you can also specify the minority carrier lifetimes. On the Gummel plot, you can basically specify the energy range in which we're sweeping the voltages, and then you can specify the output characteristics for the IC VCE curves, etc. So I did go and modify this doping to be equal. I'm going to hit simulate, and it will assemble an input deck and run PADRE. And in this case, somebody has run this particular simulation before, and instead of rerunning the simulation, what happens is we recall or call from a stash of simulation results. We pull in the results. As you've seen, I can change the size of these windows here with on the bottom right. So here it starts out with the doping profile and the electron density. The electron density and hole density. You can look at the electrostatic potential. The energy band diagram is a bit more interesting. So here is your NPN band structure. Here's the intrinsic level here, and sorry, this is the Fermi level, quasi-Fermi level for electrons, and here's the intrinsic level. All right, so what might be more interesting is the Gummel plot, where we plot the IC and the IB versus the base emitter voltage. And I'm just going to pull in a slide that I have in my class when I teach this semiconductor fundamentals course. I'm going to swap the display. So here's the Gummel plot explanation that I have in my class, and you can calculate the IC as a function of various parameters in the BJT, and the base current, and the ratio between those two is the current amplification, the beta, or DC gain. And if you look at this expression here, the beta can be read off here on a log scale as this difference here. So if you wanted to have a high gain, there's a couple of things you can do. Just from analytical expressions, you can increase the emitter doping, you can decrease the base doping, you can mess around with the emitter depletion regions, and the base depletion region, and you have the diffusion coefficients here, dN and dP. Ni is the intrinsic carrier density. That's really a material constant. So in the class, I can mess with different materials. This BJT tool does not allow you to do a heterostructure, so we can't really modify things. So let's focus on the simple things here of modifying, say, the emitter doping. Ramping up the doping by a factor of 10 should get us a higher gain of a factor of 10 ballpark. So let me X out of this. And first of all, so here is, we can read this off. We can look at it graphically. There's also an output of the beta. And the beta hovers here for higher currents at around, what is this value here? Let's see, 15. So you can hover over these discrete points. So it's roughly 15, maybe up to 18 right here. All right, so let's go in and ramp this up I'm gonna ramp it up by a factor of 20. And ramp up the emitter doping and run this. And I'm not sure if I had run this before. If I did, it should pull out a simulation result, but I didn't. So this is running a new simulation. So now you actually see PADRE solving fully the normal drift diffusion equations in this heterostructure, in this BJT, as a function of various voltages. This typically takes a minute or so on typical structures like this, these 1D type devices. If you run 2D calculations, it's going to be a bit more expensive to calculate, but it's still within minutes or so. It's now assembling the results that came in out of the old Fortran code, is massaging the results so they can be displayed. And so here now you see the modified electron density. So I had cranked up this to 2e17, and the electron density is here in its equilibrium. And then you see the base region, and then you see the collector region. If we look at the energy band diagram, we can see also here that the doping levels are different. And there is somewhat of a shift here due to the different doping level in the collector. I can also look at this at energy band diagram at final bias. You can really see how the bias is applied, how it drops in the collector. and you actually see quasi-Fermi levels of electrons and holes. So here's the electron quasi-Fermi level, here's the hole quasi-Fermi level. And we were talking about the Gummel plot. So here we are. You can, this is the new simulation where I ramped up the doping by a factor of 20 in the emitter. And here's the previous result. So what you see is that actually the collector, the emitter current is roughly the same except for the higher biases. And so you can switch between these simulations, or you can put them all on the same scale by clicking the all button here. So basically what increasing the emitter doping has done, it has reduced the base current, that is the back injected base current into the emitter. So we can now compare also the common emitter output characteristics. So let me turn, this is the second simulation where we had higher doping. And here you have the collector current in the first case, in the second case. And now we can look at the beta as well. So here's the beta. We have cranked this up by a factor of 20. Here was the first one, so let me compare those. So we went from 18 or so to 442. And that's roughly 20, right? So while these analytical formulas are great, you can also see that a realistically distributed device behaves slightly differently. You can explore that with the students. You can here we can change, for example, the base to a lower doping. We can also ramp up the emitter to 18 and should get a much higher gain. And maybe we can ramp this up a little bit here by 20 and ramp this down to very low doping, maybe 8 or so. It's probably already quite low. And then simulate a more asymmetric design where you're also messing with a collector doping. So this I certainly haven't run, so it's running the BJT simulation again, and it should give us an output characteristic here in a minute. So it's an iterative calculation on the inside, so you can't necessarily always predict how long such a simulation will run. So here are the variations we have performed. Let me turn off the all and look at the common emitter output characteristics between the three simulations. And it looks like I have flattened out these curves. And if I look at the Gummel plot in here, you can compare these three simulations. So the middle solution was actually getting us the highest on current, close to the highest on current. And if we look at beta, so we are reaching a higher beta in the last simulation, and where the beta is running up to higher currents, and then it turns off. So you can play with a lot of design concepts. You can, if you're wanting to send students into projects and study more, you can change some of the minority carrier lifetimes, which ultimately would influence these parameters dn and dp. So you can change parameters in there as well. So you can really let students loose on trying to design a good BJT that is reasonably realistic, and then you can let them loose also on more realistic structures, as I mentioned, to have a discrete type device, or PNP, etc. So what I've done in my class, I hand out homework assignments to play with this tool, and I haven't let them do projects with this tool. I had focused on the nanowire tool and on the quantum dot lab, where I let them design other things. So, but this tool would be lending itself for such exploration, and we're sort of taking in 23 minutes now, which is roughly halfway. So I'd say I'd like to invite questions.
Yeah, so our first question is, changing the doping will affect the carrier mobility. Is this taken into account automatically, or do we need to change it manually?
I believe this is taken care of automatically. And why I say that, there is mobility models. So here is actually the input deck that underlies all of this. This input deck is assembled by this app and then shipped to the tool. And I don't speak PADRE per se, but I wanted to highlight that there are mobility models that are turned on. Let me see. I think it's on the top here. And these mobility models should have doping dependence on built in. And then it still has minority carrier lifetimes as another component of the mobility.
All right, the next question, could a polycrystalline material be simulated?
Yeah, that's a very good question. Let me see. I don't think so. Yeah. In principle, yes, you can take this input deck and ship it into the copy and paste it into the PADRE tool. So in principle, you can, I didn't say it in the session, so all of the outputs that we have, you can click on this download arrow, and you would get, if it's textual output, you get this textual output. If it's graphical output, you can download graphs like this as well, and download them in different forms as data or as images that are well formatted. But so the best answer I have is we would need to look at the PADRE manual, and then take this output log, or there might be. So if I go to NanoHub tools, PADRE, and launch it. So here, yeah, we can actually add a BJT into the list. So here, what you could do is you can actually copy and paste in or upload an input deck that would be modified from the BJT tool, and then you could, in principle, run poly materials. But that's right now not in the BJT tool. I'm sorry.
All right, the next question, is it possible to integrate it with PSpice?
There is no direct path. You can say export some of these curves and then run them as fitted curves into PSpice. We don't have PSpice on NanoHub. We have an early version of Spice F3 something, but we have not built a pipeline to feed one into the other. So with that, we'll close the session. So thank you, everyone.